we talk about NP a lot because there's so many kind of optimization and planning problems that are naturally NP complete. And so it's historically something that people have cared about a lot. And a lot of the effort has been devoted to NP. But what about quantum computing? So can we do the same thing for BQP? Can we find maybe a complete problem for a BQP? Can we say that this is BQP complete, and so it's unlikely to have a polytime solution? So the natural complete problem for BQP, kind of analogous to circuit sat, is called quantum circuit evaluation. And the problem is the following. So the input is a circuit U. Let's say it's on n qubits. Let's say it starts in the 0 state, applies n squared gates, and measures at the end of those n squared gates, it measures the first qubit. So that is the format of the problem, and the particular input will specify what those n squared gates are. Okay? And we're promised that the probability of getting output 1 is either greater than 2/3 or less than 1/3. And we want to determine which is the case. Because remember, for BQP, these are only problems where we get the answer right with probability at least 2/3. And so what that means is if the answer is yes, we get, if the answer is 1, we get 1 with probability at least 2/3. If the true answer was 0, we should get the output 1 with probability less than 1/3. So we should always see outputs. We should never see things that are kind of in the middle. We should only see things that are more than 2/3 or less than 1/3. And this condition here is called a promise. Remember, I talked about promise problems last time. I said they're not defined in all inputs. So in this case, I only wanted to find this problem on the inputs that have this property. It's a very non-trivial restriction. Might be hard to evaluate. But promises don't have to be easy to evaluate. I just want to restrict my attention to this and say what that means is to solve quantum circuit evaluation, I only need to solve it on the inputs that have this property. Okay? Then I'd be happy to just solve it in those cases. I claim that this is BQP complete. So first of all, I claim it's in BQP. Why is that? Well, if I'm given this as input, I just run the circuit and I measure, and I use the output directly, and I'm promised that the output has probability, at least 2/3 of being one thing or the other, and so that output, with error probability less than 1/3, I can distinguish which is the case. And if the way I've run it has introduced more errors, let's say from the Solovay-Kitaev theorem, I could just amplify. I could just repeat it a few times and drive my error probability below 1/3. So it's in BQP. On the other hand, any problem in BQP can be expressed in this way. Right? If I have something in BQP, practically the definition of BQP is to say, there exists a circuit that does something like this. You might get nervous. You might say, well, BQP allows me to run in time polynomial in n, like maybe n to the 17. And this only allows me n squared gates. I had to pick something concrete, so I picked n squared. Does anyone see how to get around that problem? It shows you, I think, some of the subtleties of a polytime reduction. Remember, that's what we need for hardness, right? We need there to be a polynomial time reduction from any problem in BQP to this one. the number of gates here is defined in terms of the input to this problem. So I say, here I have this many qubits and this many gates. And so I start with my original n, and then I might need to n to the 10 gates. And then I have some new n prime, which is the length of this output, which could be like n to the 20. And then I've got n prime qubits and n prime squared gates. And that budget is more than enough to accomplish what I want. So the answer basically is this polytime reduction. Seems very innocent, but it can smuggle in polynomial overheads. The length can get polynomially larger. And so it's one way to think about this is it's a very crude notion of complexity. As a practical matter, I care about the difference between n squared and n cubed. But this crude notion of complexity will really just tell me if it's like polynomial versus exponential. Right? It will maybe a little bit more than that. But it's not going to distinguish between different kinds of polynomials. And so that's why I can say very crude things like this. And it's enough to give you kind of a first-order answer. And if you refine the same techniques, you can get a more refined answer as well.